Thank you very much. Everyone can hear me? Okay. So today I'm going to tell you about a new way to look for particles that are not yet discovered through observing black holes and gravitational waves. Today we are lucky or unlucky, depending on your perspective, to live in the age of the standard models, where we have a set of parameters that very accurately describes the expansion of our universe and the fundamental interactions within it. These have been extremely successful, from excellent agreement between theory and experiment, such as lambda CDM matching very well to observations of primordial fluctuations in the CMB, to major discoveries like that of gravitational waves, which are already teaching us a lot about the universe. On the particle physics side, there have also been great discoveries, such as the Higgs boson, and great agreement between precision calculation and precision measurement. However, we all know that's not the full story. There's many problems that remain. In particular, the lambda and the CDM and lambda CDM are not well understood, both from the particle physics side as well as from the cosmological side. What is the particle that makes up the dark matter? How does it behave on short scales? These are all issues that we are facing today. From the particle physics perspective, there are different ways to try to address these problems. One way that we've tried in the past is by looking at symmetries and conservation laws of fundamental interactions. So these are central to the way that we understand short-scale physics, and they can be continuous, such as in a translational symmetry that leads to momentum conservation, or they can be discrete, such as a parity transformation that flips all the directions to their opposite in spatial directions. So these are a class of symmetries in which we use to understand the fundamental particles and interactions, and they've been very useful historically in solving problems that have been brought up experimentally. For example, almost a century ago now, Pauli proposed the neutrino. At that time, he called it the neutron, to preserve energy and momentum, which arise as the conservation of which arises from the continuous translation symmetry in beta decays. So beta decays, the electrons coming out from beta decays did not satisfy energy and momentum conservation before the addition of this new ultralight particle that was the neutrino. And as soon as 8 years after this first proposal, once Fermi had written down his interaction of the four Fermi interaction between neutrinos and other particles, these interactions were already being used to understand theories of stellar nucleosynthesis, where the neutrino was a key ingredient of the fusion going on in the sun. This was 20 years before the neutrinos were first discovered in a laboratory experiment in 1956. And this is not surprising that the effect of neutrinos was first seen or theorized in the sun, because in addition to being solutions to this theoretical puzzle of momentum conservation, theoretically neutrinos were postulated to be very light and very weakly interacting. They were the interactions are suppressed by a very high energy scale, and this makes it very difficult to detect them in laboratory experiments. And they require high energy densities and large numbers to be detected. So it's not surprising that our best evidence and some of the things that we've learned the most about neutrinos come from astrophysical observations. For example, we've learned about neutrino oscillations from looking at the sun, neutrinos coming from the sun. We've observed neutrinos from supernova. And right now, the best constraints on the sum of the neutrino masses is also coming from observations of temperature power fluctuations in the early universe. On the other hand, neutrinos have also helped us understand some of these objects. For example, measuring the neutrino flux from the sun is providing key insight into the processes that go on in the stellar interior. Now, of course, while people might have thought that neutrinos could also be a solution to the dark matter problem, they're not good candidates for the dark matter of the universe, and so there's still work to be done. In addition to the experimental problem of dark matter, there's also outstanding theoretical issues in particle physics, and that's what I want to focus on for the rest of the talk. I'll spend some time motivating new ultralight particles, even lighter than the neutrino, that are well motivated in theories of particles beyond the standard model. And then I'll discuss how to look for them in astrophysical objects, in black holes and gravitational waves. And please feel free to interrupt with questions at any time. So going back to the story of symmetries, I want to go back to the symmetry of parity that I mentioned at the beginning. It turns out that the standard model is very bad at preserving parity. And in fact, you expect significant amount of parity and actually what's called CP violation in the potential of the strong interactions. And that we know from other measurements. However, if there were such a strong violation of this CP symmetry, this would give a dipole moment, electric dipole moment, to the neutron. So even though the neutron is electrically neutral, it would have a overall small dipole moment. And we can see why this is the case. Let's look at the neutron. Mu is the spin and d is the dipole moment. So how does this behave under a parity transformation? So remember I said the parity flips all of the directions to their opposite. So that means that the dipole moment, which is just a vector, would change sign, whereas the spin, which is a cross product of two vectors, would change sign twice and remain in the same direction. So that means that if parity were a good symmetry, then the dipole moment would both be parallel and anti-parallel to the spin, so that means it has to be 0. So if we measure a dipole moment of the neutron, that implies that parity or CP is not a good symmetry of the model. You can try to do an estimate of what is the size of the expected dipole moment of the neutron. And for this, I'll do a cartoon picture where you can think of a neutron as just a ball of quarks. This is not what it actually is, but it serves the purpose. So you have the dipole moment you can just calculate classically as the sum of charges weighed by their distances. That's the definition of dipole moment. And the size of it is just estimated by the size of the neutron, which is about a Fermi, times the typical charge, which is over the electron charge. So you expect this to be about 10 to the minus 13 e centimeters if all of the quarks are evenly distributed. Now, if theta is a parameter of the standard model, you can do the proper full quantum field theory calculation and find that the expected dipole moment is actually a couple orders magnitude smaller. This is because there's a small charge that's associated with emitting this photon, and there's a loop factor and so on, but this is well understood. So there's a dipole moment is proportional to theta, which parameterizes the amount of parity CP violation in the standard model. Like I said, this is a parameter that describes this interaction, and we can look for it in the laboratory. In fact, we have an experimental upper bound on this theta parameter, which is 10 to the minus 26 e centimeters. It's about 10 orders of magnitude lower than even the full field theory calculation tells us. So this means in this cartoon picture, all of the quarks would be perfectly lined up to within 1 part in 10 to the 10, which to a particle theorist is a huge unexplained tuning, given that there's no good symmetry enforcing this arrangement here. Now, if theta is a fixed parameter, there's no way around it. It is what it is. But there was a very elegant solution that was proposed over 40 years ago now that explained this issue. And it says, okay, let's take this parameter and turn it into a dynamical field. So just like, for example, in a molecule, the angle between the oxygen atoms and the carbon atom can fluctuate and can relax to a minimum energy configuration, which in this case is parallel. If the theta parameter of the standard model is also a dynamical field, it can relax to its minimum, which turns out to be the value where Cp is not violated or is not manifested in the strong interactions. So, and this theta angle has become known as the QCD axion. It's this light particle which explains why there's no electric dipole moment of the neutron and comes with many observable consequences. The axions, as I said, are solutions to this theoretical puzzle of what's called the strong CP problem. And it's a very predictive model, which is parameterized by one high-scale parameter, Fa. So they interact very weakly, and their mass is very light. It's inversely proportional to this high-scale Fa. So the masses that I'll be focusing on are in the range of 6 × 10⁻12 electron volts. As I said, they're extremely weakly interacting. They're also excellent candidates for the dark matter of the universe. And because they're so light and weakly interacting, just like neutrinos, they're best constrained by evolution of stars and supernova, as well as other astrophysical and cosmological observations, rather than laboratory experiments. This is the parameter space that I'll be focusing on today. So here the x-axis is the mass of the axion in electron volts, and the y-axis is the coupling Fa. So stronger couplings is higher. The green line here is this QCD axion that I described. It solves the strong CP problem of the standard model. And the gray regions are current exclusions, mostly coming from, for example, supernova 1987A. The fact that we saw a neutrino burst tells us that there was not more energy loss from the supernova coming from axions than from neutrinos. So that's here. CAST is an experiment that looks at axions coming from the sun. There's telescope experiments looking for axions decaying to photons. And there's one experiment here that's looking for axion dark matter here on Earth. So there's still a lot of work to do. As you can tell, most of this parameter space is wide open. And today I'll be talking about how to look for very light, very weakly interacting particles that couple to us and to each other as weakly as gravity. So you can see the scale of Fa here is of order what's called the Planck scale. And I'll be doing that by using black holes. So for reference, on the top axis, I'm showing the wavelength of the particle. And here it's about 10 to the 5 kilometers because they're so light. The wavelength is very, very long. And it corresponds to a 30 solar mass black hole radius. If you come to my talk at NYU on Monday, I will also be discussing how to fill more of this parameter space by considering other interactions of the axion particle, either with light, with an ongoing laboratory experiment that I proposed, or by looking at axion waves that are emitted from similar systems that I'll be discussing today. So to explain how you can use black holes and gravitational waves to look for axions, I first have to tell you about a process that's called black hole superradiance, which is a mechanism to rapidly extract angular momentum from rotating black holes and place it into large energy densities of particles in its vicinity. You might be already familiar with a similar process called the Penrose process, by which you can extract energy from a rotating black hole. If you throw in a particle into the ergosphere of a rotating black hole, it can split into two pieces. And since the ingoing part has negative energy as viewed from infinity, the outgoing part can come out with more energy than the energy with which it came in. This spins down the black hole by a small amount, and it extracts some of its energy into the kinetic energy of the particle. The same thing can happen for waves. So this was realized by Zildovich and others in the early 70s, that if you have an incoming wave that scatters off of a rotating black hole, it can come out with a larger amplitude than the one with which it came in if the angular velocity of the black hole is large compared to the angular velocity of the wave. And again, it can extract this energy by slowing down the black hole through the dissipation of the wave at the black hole horizon. And this happens when the superradiance condition is satisfied, the black hole is spinning fast enough compared to the incoming wave velocity. This is a numerical GR simulation by Will East, who I talked to a lot while I was at Perimeter. He does these beautiful numerical GR computations. This one in particular is a rotating black hole, and you'll see an incoming wave in blue. That's an incoming gravitational wave. And it gets rescattered into an outgoing red gravitational wave. You can see the amplitude is much increased because of the extraction of angular rotation from the black hole. Now, this is great. We know it happens in GR, but it's a one-time process. The wave comes in, it leaves with a bit more energy. There's no really big effect on the black hole itself. However, it was realized in the 70s that this process could become exponential if the wave has a small mass. So if you have this black hole and you have a particle whose wavelength is of order of the size of the black hole, it can form bound states, just gravitationally bound states around the black hole. And if those bound states have the right angular velocity, then the superradiance process will apply and those bound states will grow. For stellar mass black holes,
Sorry,
yes?
I feel like I'm being stupid, but when you say angular velocity,
yes, yes, thank you. So what I really need is the phase velocity. So what you're comparing is if you write the field as, e to the im phi minus I omega t, it's omega over m. So it's the phase of the particles in the state. So it could be a plane wave or
essentially a frequency.
It's the frequency modulo the angular momentum number. Yeah. It's basically that you're comparing the rate of change of the time derivative to the azimuthal derivative. Yeah, and I'll ask me again if it doesn't make sense when I talk about the bound state specifically. Good. Okay. So there's these bound states, and it will turn out that the rates are most efficient when the wavelength of the particle is of order of the black hole size, which means that for particles that are, say, 6 times 10 to minus 11 eV, like the axions I described, you want the black holes to have sizes of kilometers or larger. Going back to what these bound states actually look like, I want to remind you of what a typical 1 over r potential solution is. It's just a solution for a hydrogen atom, right? You have proton, and then you have an electron in orbitals around the proton through the electromagnetic force, which is parametrized by alpha and m. In the standard model, it's 1 over 137 approximately. And these bound states carry quantum numbers, like the principal and orbital quantum numbers, NLM, making up different energy density configurations. And the typical radius is given by 1 over the coupling, alpha ENM, and 1 over the mass of the electron, which is about an angstrom for a hydrogen atom. For the black hole, when you're far enough away from the black hole, the potential is also 1 over our potential, so we can directly apply these results for the non-relativistic scalar fields like axions that are sitting around the black hole. You have a instead of alpha ENM, which is 1 over 137, now you have the product of the black hole size and the particle mass times, the black hole size times the particle mass, which you can think of as the ratio of the black hole size to the particle Compton wavelength. The radius is a few to a few hundred black hole sizes. And the big difference here from the hydrogen atom is that axions are bosons, and also they're extracting huge amounts of energy from the black hole. So unlike just one electron per level in hydrogen, you can get 10 to the 75 or 10 to the 80 particles all in the same state. So these are what the bound states look like far away from the black hole. Now the fact that there's a black hole at the center actually changes the energy spectrum. So typically for a hydrogen atom, you have energies, there's the rest energy of the electron minus some binding energy because of the electric potential. Here you also have the rest energy of the axion. The mass is given by mu here, minus some binding energy that's proportional to this gravitational potential. And then there's an imaginary part of the frequency that corresponds to the interaction of the field at the black hole horizon. And this imaginary component can be positive or negative depending on whether the superradiance condition is satisfied, so depending on this angular phase velocity of the particles in the state. Yes?
Is there a capture probability?
Good question. So, I mean, in principle, yes, you can capture particles from infinity if they have the right velocity. However, the process here is very unique in that it's actually can grow from zero abundance of particles in the black hole vicinity. So it's a classical instability of the black hole. That means that even if there's quantum fluctuations of the field, of the axion field in its vicinity without assuming any cosmological abundance, this growth will take off and become exponential very quickly. Okay, so what do these particles do to the black hole itself? Let's say you start with a black hole that's born with high spin, say 0.95 dimensionless units, which is close to extremal Kerr, and some large mass, let's say it was born in a LIGO merger. The blue regions here are showing the range of parameters where the superradiance condition is satisfied. So that means for particles with angular momentum L equals 1, 2, and 3, the black hole is rotating fast enough so that it's rotating faster than the particles in the cloud. With the parameters I've picked here for a 6 times 10 to minus 13 EV axion, the black hole will spin down in about a year's time. Yes?
So what is the, I guess in order to calculate this spin down, you have to know the amplitude of the scalar wave that you eventually get?
Yes, so the
so
spin...
you talked about the linear instability, where you basically grow the field, but where does it stop? I mean,
Yes.
First of all, what is the time scale and where does it stop? How does the time scale compare to the spin period of the black hole?
Good. So the time scale is given by the superradiance rate, and that is calculated just by doing you can calculate it analytically by doing a matching calculation of these fields at large distances to the fields close to the horizon. And it typically is about 10 to the minus 6, 10 to the 6 times longer than the light crossing time of the black hole. So there's a kind of a small overlap coefficients and large powers of the small alpha parameter that enter, but the dimension full scale is the light crossing time of the black hole. So the parameters I picked here, I think alpha is about 0.1, and it takes roughly a year for this to happen, which is actually about 180 e-folds of the superradiance rate. So you start from 0 particles, the number of particles grows exponentially. I'll get to it in a second what stops it. And then as the number of particles in the cloud gets large enough, they extract angular momentum from the black hole, and that sets this overall time scale.
Is the picture we should have, is there's a vacuum fluctuation, one of the, like with a pair of axions maybe, and one falls in, and the, I'm getting a little confused about whether I should think of this as just a flux of axions.
Yeah, you don't need to think about anything necessarily falling into the black hole. I mean, it's true that at the horizon, technically everything is getting absorbed, but you can just think of each of these bound states has some occupation number of 1/2 h bar omega at all times, and that gets enhanced.
The nice question, where do they come from? You're talking about the states existing.
The states are just solutions.
A black hole is born at t equals 0.
Yeah.
Where did the axions come from?
the axions come by extracting energy from the black hole itself. So there's existing just empty bound states that are solutions to the equations, right? And then because we know quantum mechanics works, or because there's some extra energy density in the vicinity of the black hole, there's a non-zero occupation number of each of those states, which is at least 1/2 h bar omega. And that gets amplified up by extracting this rotational energy from the black hole. Did I answer your question? Okay. So this growth becomes exponential, and to answer the previous question, it stops at the point where order 1 of the black hole's angular momentum has become extracted. So the black hole going from a high spin of 0.95 to a slightly lower spin of, say, 0.6, you can calculate how much angular momentum there is in the black hole, which is just gm squared. If you convert that into h-bar units, that's 10 to the 78 units of fundamental angular momentum units. Each of the axions carries 1 unit of angular momentum. So at this point, there's 10 to the 78 particles in the cloud, and the black hole has spun down by order 1. And now it no longer satisfies the superradiance condition because the black hole and the cloud are co-rotating, and so that's what stops the growth, yes.
So it's just ignorance, but to an astrophysicist, this sounds very strange.
Yes.
And you spin down black hole by an order of, if you look at unstable modes of stars, typically if the growth rate is 10 to the minus 6 of the oscillation frequency of the mode, it saturates at 10 to the minus 6, not at unit.
The question is what is the process that stops the growth, right? So here, the mass of particles that's in the cloud is still fairly small. It can be up to a few percent in the extreme cases, but usually it's about 10 to the minus 3. But in principle, this is just a purely gravitational process. So the only thing that shuts off is the back reaction on the black hole itself. It can be much smaller if say you start up here, then you only have a tiny way to go until you get to the superradiance condition. I agree, it's a very unintuitive process. It's also very cool. And I'm happy to talk about it at length if you have more questions. Is everyone on board? Okay. So the other very cool and possibly non-intuitive thing is that you have this huge energy density in the cloud, and that can actually source gravitational wave radiation, which is observable at LIGO. And I'll talk about that in a few slides. But for now, it turns out that the gravitational waves will deplete the first level, so it'll cause the occupation number and the level to decrease with time. And at that point, the next level will grow. This level has angular momentum too, so since it has an angular momentum barrier, it's localized further away from the black hole, which means that the growth is parametrically slower. It has less overlap with the black hole horizon. And now instead of taking 1 year or 10 years, depending on the parameters to grow, it takes about 10 to the 6 years. And the gravitational wave annihilation signal for these parameters will last as long as 3,000 years.
All this just scales with UA, right? So this is now with the axion scale close to the Planck scale.
That's correct. So all of these time scales are linearly proportional to UA, and they're also parametrically dependent on the ratio of the black hole size to the axion wavelength to a higher power. Yes. So this is Planck scale axions exactly. At this point, the growth of the cloud has stopped. In principle, the next level out can start to grow, but that one is, again, parametrically slower, and astrophysically it won't have an important effect because other things like accretion or just the age of the black hole will start to dominate the evolution of the black hole spin. So that's the story of what happens to a black hole in the presence of these axions in the theory. And in the next part of my talk, I want to discuss the observational consequences. First, I'll talk about how, since the black holes spin down, looking at spins of black holes can teach us about the parameter space of these ultralight particles. And second, I'll talk about ongoing continuous gravitational wave searches that are looking for signals from these clouds. So this is the same parameter space I was showing before. Here's the black hole spin as a function of black hole mass. The blue regions are the ones that are affected by superradiance, now for a particle that I expect to be 10 to minus 11 eV. And there are already measurements of black hole spins and masses that we infer from observations of black holes and X-ray binaries. These are the black holes here shown with their corresponding error bars. And I've used these measurements to exclude parts of the axion parameter space based on the fact that if superradiance were happening, if this particle existed, then all of these black holes would be expected to spin down to the bottoms of these curves well in the age of the black hole. So each of the black holes sets an exclusion region shown in blue on a range of particle masses. This is the axion mass here shown in EV. And the combination excludes about a factor of 30 in axion mass. The different regions correspond, just show you how different angular momentum levels contribute to the exclusion.
I'm sorry, the horizontal axis there is mu A?
Yeah, sorry, the label fell off. Yes, it's mu A in electron volts.
And this is for the QCD axion.
So this is assuming a gravitationally interacting particle, which is a good approximation. As David was saying, it's it's a Planck scale interaction that's expected. Yeah. Of course, in addition to the X-ray binaries, we now have a wealth of new black holes that we've observed in mergers at LIGO. And if a light axion exists, the initial merger black holes are expected to have low spin because of the superradiance process. And if they can spin down within the age that it takes the black holes to come together through gravitational wave radiation. So here is a cartoon population of all the black holes that are merging in the local universe. In the presence of a ultralight axion, all of the black holes that were born with high spin are expected to spin down to these characteristic superradiance lines. So what you expect to see is a non-trivial spin mass distribution with an extra overdensity of black holes on the line set by the superradiance condition, which are a function of the axion mass. And I've done a toy statistical analysis to see how many black holes you would need to infer the fact that the spin distribution is non-separable, so there's some dependence on the spin distribution is different depending on the mass of the black hole. That was not necessarily proof for the existence of an axion. That might just be telling us about just different astrophysical formation channels, but it would be an interesting hint that something is going on. So if you take hundreds to a few hundreds of black holes, depending on whether they take 10 million years to merge or a billion years to merge, you might need several hundreds or 100 events to reach this conclusion with the current LIGO, typical LIGO spin error bars. This was something I posted in 2017. Recently, there have been some analyses looking at a different statistic at the events that have already been observed at LIGO. They've concluded that there's not enough evidence yet, either for or against the existence of a light particle. I think so far they just looked at one example of a particle mass at 10 to the minus 12 eV. But so far we have 10 events on tape, so I think this is going to get very interesting in the next few years now that we're seeing one merger per week or so. That could give us enough information very soon to start doing these kinds of more detailed analyses. Any questions on the black hole spins? Yeah.
So for a given axion mass scale, you asked what is the characteristic range of masses that we can rule out on logarithmics?
Yeah. So for a given black hole, so let's go back to this plot. So for example, so here I'm varying the black hole mass on the x-axis and fixing the axion mass. So, but you could invert it because the main parameter that's characterizing it as just the product of the two, of the axion mass with the black hole mass. So if instead I'm plotting the axion mass on this axis, then it would cover a range of, say, a factor of 10. So one black hole could cover axions within about a decade.
A decade.
Yeah, and it depends on, basically it takes longer, as you go to lighter and lighter axion masses, it takes longer and longer to spin down, so then it depends on the sensitivity of your measurement, or it depends on how long the black holes have been around. So in principle, you could even go to a factor of 100. But here you can see for each black hole here, that's one mass, and it's covering about a factor of 10 or more in axions. Yeah.
What about massive black holes, like at the center of, are you going to talk about that?
I won't have time to talk about it today, but the qualitative story goes through in the same way. So you can, with supermassive black holes, you can look for even lighter axions. Basically, if you change the black hole mass by a factor of, say, 10 to the 6, you decrease the particle mass by a factor of 10 to the 6, and you get the same effects. You get spin down, you get gravitational radiation, which may be observable in LISA. The one big difference with supermassive black holes is that they're usually accreting, and that's a significant impact on their evolution. And since the particle mass is lighter, all the time scales, which are proportional to the axion mass, get longer. And so then the process of spin down through superradiance becomes comparable to the rate of spin up through accretion, and that needs to be taken into account. So the dynamics are a bit different, but in principle, the whole story will go through qualitatively in the same way.
These ones are also accreting, right?
These are accreting, but the time scale for superradiance here is about a year, whereas if you multiply that by 10 to the 6, that becomes much closer to the Eddington time scale. Yeah. Good? Okay. So that's what you can do with black hole spins. Now turning to the last part of my talk, which is gravitational waves. As I said, these clouds carry a huge amount of energy density, and they're also oscillating with a characteristic frequency, which is twice the axion mass. From the particle physics perspective, you can think of this as two particles, two axions coming together and sourcing a gravitational wave. But you can also just calculate classically this energy density, the stress energy tensor of this field, and find that it's oscillating at twice the mass of the axion particle. Here I'm showing another full GR simulation by Will East, which is showing this cloud sitting around the black hole emitting gravitational wave radiation. So you can see that overall there's a large energy density, and there's a subcomponent of that energy density which is rapidly oscillating. And that's the component that's sourcing the gravitational wave radiation, and it's proportional to basically the velocity of particles in the cloud.
So
Yes.
just make sure I understand. These are axions emitted by the black hole. This doesn't matter if the axions are not the dark matter.
Exactly, yes. So now we form these clouds of axions, and they're emitting gravitational wave radiation. How does the power and time scales depend on the parameters of the problem? Remember, I was talking about this dimensionless alpha parameter, which is the proportional to the mass of the axion and the mass of the black hole. The larger alpha is, the more tightly bound the cloud is to the black hole, and the more energy it has. So that means the power of the gravitational radiation increases. The strain actually increases as alpha to the 7th power. Now, because there's a finite amount of mass that it can extract, if the power is larger, the power emission actually lasts for a shorter amount of time because you just run out of energy. And so the time scale on which the gravitational waves are emitted scales as a high negative power of this alpha parameter, as alpha to the minus 15. So if you have, say, for a given black hole, if you have a heavier axion, you'll get larger strains but shorter signals. And the signals are just very simple sine wave at twice the frequency of the axion mass, and they go on for a very long time set by this time scale of gravitational wave emission.
So this is a single black hole.
This is a single black hole.
Surrounded by its wave function of axions.
Exactly.
But if it's in, so it.
The waveform will be more complicated if, say, the
Why
black
doesn't
hole's in
this
a binary or.
Undo your or is. kind of connect this to the previous argument. Is this another way of thinking about the previous argument about spinning it down?
Ah, good. Yeah, so that's something I didn't mention, which is very important, which is that the time scale associated with the gravitational wave emission is parametrically slower than the spin down time scale. So though it scales as more powers of this alpha parameter. So first you grow the cloud on the time scales that you're growing the cloud, the emission is basically negligible, and then over a longer time, it'll deplete the cloud. Yeah.
So the black hole at the center of this cloud is already not spinning.
Correct. It's slowly spinning. Yes, that's correct. So it's already spun down, and now you're emitting gravitational waves. Yeah. So this very fast parametric dependence means that there's two broad classes of signatures. There's very weak, long signals, which can last for thousands or even billions of years, but they're quite weak, so they're only visible from black holes in our galaxy. Or there's loud, short signals, which last much less time, but they can be observable from far away, like tens or hundreds of megaparsecs. And so one thing you can do is you can look for follow-ups of black hole binary and neutron star mergers. You know that forms, especially for black hole binaries, you know that forms a rapidly rotating black hole. And you can follow up to see if you get this monochromatic continuous signal afterwards. We found that the event rates are not super promising at current sensitivities just because the strains are not loud enough to follow up all of the black hole mergers. But at future observatories that will hopefully come online in the next decades, there will be up to hundreds of such signals, which would be a really beautiful test of this model because you can measure the mass and the spin of the black hole that formed. You see the frequency that's coming out. You can trace the power as a function of time, so that will really give you a complete picture of what's happening around the black hole. And there's a group led by Max Sisi who's looking at these types of signals, building pipelines for the LIGO data, and they kind of agree with our conclusions, but I think it's interesting to already start looking at these signals in the current data. So for the last few minutes, I'll focus on these signals, which are more near-term prospects, and some work I'm doing with a continuous waves group to try to detect these signals in current LIGO data. What do these signals look like in practice? So let's take a particle that's 8 times 10 to minus 13 electron volts in the range we've been discussing. Here I'm showing the strain as a function of frequency of the gravitational wave. So the dashed line here is twice the axion mass. As I said, the gravitational waves are approximately at twice the energy of the particle. And the orange lines indicate for a black hole of a given spin, a very high spin or a slightly lower spin, what the strain would be from such a system at 1 kiloparsec away. If you take an older black hole, the strains decrease simply because the gravitational wave emission is slowly dying off as all the axions are annihilating away into gravitational waves. So it's better to be looking for younger black holes. Now, what does actual population of black holes appear like in this plot? We are using a kind of a cartoon simulation of black holes evolving through the Milky Way. So they're born in the disk or the bulge with some kicks. They move around in the galactic potential, and they show up as a particular distribution in the galactic plane with a large set of different velocities. The positions and the velocities are the quantities that we'll care about in terms of the observations, and we assign black hole masses and spins according to some simple distributions. We have the kind of standard distribution that we use is a power law Salpeter mass distribution between 5 and 20 solar masses for black holes in our galaxy, and we choose a uniform spin distribution just for simplicity, but we also look at heavier black holes as well as lower spins to see how the results change. So these black holes now are populating the space under these curves. So each black hole is at a distance that's further than 1 kiloparsec, so it'll be sourcing a weaker signal. So each of these dots is a single sinusoidal wave in the frame of the black hole that's at order of twice the axion mass. The reason why it's smaller than the axion, twice the axion mass, is because of the binding energy of the cloud to the black hole. So that creates a negative binding energy, which shifts the frequency to a lower value. And that shift depends on the mass of the black hole itself. So the heavier the black hole, the lower the frequency, but the bigger the strain, because this alpha parameter increases. So that's the distribution as seen in the frame of each black hole. Of course, the black holes are moving, so there's also a Doppler shift, which spreads out this shape further, and you get this characteristic pyramid-like shape in the frequency strain plane that you would expect to observe in the LIGO detector. So if you see one signal from one black hole, you expect a whole host of signals in a narrow, clustered in a narrow regions in frequency, and with a particular shape that would reveal itself more and more as you decrease the sensitivities. 5 minutes? Good, thanks. Good. Any questions on this? So if you're familiar with LIGO observations, you might remember that the merger events have a strain of about 10 to the minus 22 or 10 to the minus 21, which is all the way up here. So how do we hope to look for these signals? Well, luckily for us, these are already the kinds of signals that are actively being searched for in the LIGO data. They're called continuous wave searches, and they fit into this, the physics motivation has been coming from isometric rotating neutron stars. So if you have a neutron star that's rotating, that's not perfectly azimuthally symmetric, it will source a continuous sinusoidal signal at twice its rotation frequency. And even though these signals are very, very weak, since they're very simple signals that are coherent over long times, you can integrate for a long coherence time and gain in your signal to noise as a function, as a square root of the integration time. So compared to the solar mass black hole mergers, which are under a second long, you can integrate for hours or even days and gain a lot of sensitivity. Now the problem is that the number of templates you have to search for as you increase your coherence time actually scales as the 6th power, depending on the search, plus or minus 1, the 6th power of the coherence time. So if you're trying to do a blind search for all of the black holes in the galaxy, you need to scan over 10 to the 17 templates. That's not computationally feasible, and what's usually done is a semi-coherent search where you split up the long coherence time into many chunks, and you integrate each one separately, and then you add them together incoherently. This, of course, reduces the sensitivity of the search, but it makes it computationally feasible. And the current results are, these are from a couple years ago, reaching sensitivities of order 10 to the minus 4 to almost 10 to the minus 25 with the first run of LIGO data. So this is very impressive work by the continuous waves group that's getting these very low upper limits on monochromatic gravitational waves. If we apply these limits to our black hole population, we find that the number of detectable signals from these black holes above the current upper limits can be quite large. So the x-axis here is the boson mass. The y-axis is the number of detectable signals. And you can see that there's a characteristic shape here. At the low end, it falls off because there's not enough heavy black holes. And also here is around where you start hitting the LIGO noise wall. At the high end, the signals become weaker because the black holes become lighter. There's less energy that's being sourced by the black hole. And again, the sensitivity of LIGO is decreasing at these high frequencies. In the interest of time, I'm not going to go through the details, but the basic message is that if you have fewer rapidly rotating black holes, the number of signals decreases by about an order of magnitude if you get rid of all black holes that spin faster than 0.5. And if you have more heavy black holes, so if for example, the metallicity is a little lower and you get heavier black holes from stellar explosions, then you can get more heavy black holes and go to lighter axion masses, because bigger black holes correspond to longer wavelength particles. Depending on your assumptions about the distributions of black holes in our Milky Way, about their overall number and spin distribution, you can use this to exclude some range of axion masses. For example, if you think that all black holes are rotating, or that black holes have a uniform distribution in spin from 0 to 1, you can exclude a factor of almost 10 in axion mass. If you think there's fewer highly rotating black holes, then you exclude a narrower range. So this is something that I think will be very interesting to quantify more as we learn more and more about black hole formation and the ends of stellar evolution. It turns out that actually there can be too many signals counterintuitively. So these searches for rotating neutron stars, the pipelines are all validated under the assumption that there's going to be one signal or a couple of signals throughout the whole frequency band. But as I showed you, all of these signals from any axion mass here will be, say, almost 1,000 signals within a very narrow frequency range that's set by this small binding energy of axions of the black hole. So, for example, this is showing the spectral density of LIGO in the presence of all of these signals. This is the real spectral density, and this is what you would infer by looking at your data if there was a light axion around. And so you might try to subtract this extra noise because you think that this is part of some systematic or instrumental issue. So in some parts of the parameter space, we're going to re-characterize the LIGO pipelines to make sure that they're still sensitive in the regime of many dense signals. Okay, any questions? You can think of questions while I conclude. So in the presence of ultralight axions, I've shown you that the superradiance process can spin down astrophysical black holes. In particular, for the QCD axion close to the Planck scale, very, very light, the black holes that spin down are exactly the ones that you expect to see in our galaxy and the ones that you see merging in LIGO. And these are these black holes will have a different spin distribution than you would originally expect. They will pile up on these superradiance condition lines, and you can use this to already place constraints on axion parameter space. And the very large energy densities of axions that sit around the black hole source, gravitational wave radiation, that is already being looked for in the LIGO data. And in my work, we've shown that these hundreds or even thousands of these signals may already be observable and can be used to place constraints on these types of light particles. So we've all known for a long time that astrophysics and cosmology are the best way to look for ultralight particles because of both their precision and their huge sources of energy densities. And I hope today I've convinced you that you can go even further and use black holes and gravitational waves to continue this program of looking for new physics beyond the standard models in gravitational waves and black holes. Thank you.
Thank you very much, Masha. Any additional questions? David?
So just the parameters you're looking at are ones which always seem to me to be difficult ones for the axion to be dark matter, right? Because if you have anything like inflation, these are temperature. These are scales well above the heat temperature.
Yes, so most of these axions are produced in through the misalignment mechanism, which produces cold axions.
But then it requires a misalignment. And
Yes,
it would
so
be really small.
So it does require an accidentally small misalignment angle. It's not necessarily a huge tuning, it's about a factor of 1 in 100 or so at these scales. But it's true that it's not the generic parameter space for the dark matter. But for me, this is not a big issue because, for example, if you're producing them through inflation anyway, it's very likely that you can just be naturally in a patch of inflation where the axion field was the right value. It's a very, very mild, it's not,
Yeah.
it's a very,
Some of us get a little nauseous when we hear the word anthropic.
yes, I know, but this is a very, very mild example of that because you are naturally, so you don't have to rely on multiverse or anything, right? You already have inflation and that is automatically giving you different values of the initial conditions of the dark matter density through the axion. Yeah.
So is any of this affected, just think about the emission,
Yeah.
by magnetic fields around near the black holes? And what I'm wondering about is if I think about, photons propagating in a plasma, there's a plasmion frequency.
Yeah.
And if I have axions moving in a magnetic field, there's, the axion to photon conversion.
Yes,
of the
exactly.
magnetic field. And the photons I create would be so one wavelength
Yeah.
that they would interact with the plasma.
Yeah.
And I can imagine this flux of axions you're generating interacting with any plasma around and effectively exerting drag so that there's sort of a back reaction.
Yeah, that's
So
a
you
great,
can't- when you're coupling near the Planck scale,
Yes.
so everything's really.
exactly. So I think you've answered your own question, but
But your
basically.
masses are really low.
Yeah,
so
yeah.
I'm not doing the calculation.
Yeah, right.
I don't
So
know the answer.
exactly. So the answer is that for typical, so you can compare the flux of photons that you'd get through this coupling. So for those of you who are not axion experts, you can have an axion convert to a photon in the background of a magnetic field. And so you can compare that process to, say, the emission of gravitational waves. The emission of gravitational waves is suppressed by a power of the Planck scale, but it's also sourced by a quadratic density of the axion field, right? You take two axions to make the graviton, and these energy densities are really, really big. If you do the axion to photon, you have an axion plus a magnetic field energy density that are sourcing your photons. The typical energy densities of the axions here are capital MeV to the fourth, which corresponds to basically close to Schwinger per production magnetic fields. So you're not typically getting big enough magnetic fields to compete with that energy density.
Well,
Unless you're
magnetars.
around the neutron star.
Yeah, so you can plug in the numbers more precisely, and it turns out that for even the biggest magnetic fields, so for neutron stars, this process doesn't work as well, but for very large fields around black holes that you find, if you plug in the numbers, you find that the conversion rates to photons is subdominant to the rate to gravitational waves. There's also an extra small coupling when you talk to photons because the electric charge is small, so that also decreases the effect. Now, the plasma effect that you mentioned actually would probably cause a suppression because you're not converting to free photons, you're converting to these lossy photons. Exactly. So that also produces a suppression. But it's true, if you crank up the photon coupling past what you'd expect theoretically by many, many orders of magnitude, then this might become an important effect, but it's not in the regime that I'm talking about here.
Yeah, no, I don't think you'd emit individual photons, so what happens?
Yeah, you could heat the
plasma
exactly.
around, you
Yeah.
could drive a wind, and
Right.
that back reacts.
But the upper bound on that power is still the conversion to photons, and that is subdominant. Yeah, but that's a very good question. Yeah.
I was just wondering, so what is the time scale for the spin down for supermassive black hole? I don't have the numbers.
So it would be between, so the E-fold, the time scale for stellar mass black holes is, say, 10 to the 4 seconds to years. So for supermassive black holes, it would be, say, 10 to the 6 times that, so a year to 10 to the 4 year, 10 to the 7 years, depending on the
Okay,
mass
so it's
range.
still relatively short.
It could be short, yeah.
Compared to, say, so for example, then have you considered this scenario? If you have a supermassive black hole or heat which is not spinning very rapidly.
Yeah.
but then it's being spun up by accretion. I guess there is some critical critical spin of the black hole.
Yeah, you'd get some attractor solution, so you'd have the black hole is spinning up from accretion and spinning down from superradiance, and it would slowly travel along these superradiance lines and gain mass and spin. And we actually think it might be a way to speed up the accretion of black holes, right? Because slowly rotating black holes accrete mass faster than rapidly rotating black holes. So if you spin them down, then you can make them accrete faster. But
So maybe one final question? Yeah.
For this figure that you showed where you have sort of the mass spin plane and
Yeah.
you have certain regions excluded, if you were to say, I believe that this effect really exists, and so I expect a joint prior distribution on black hole mass and spin, how would that kind of affect LIGO's data analysis?
that's a great question. There's been a lot of work on different assumptions and the priors in LIGO data and how that affects the spin conclusions. I'm not the best person to answer that. I think the one thing that you do expect is that you should not be surprised by the fact that most LIGO black holes have been found to be slowly rotating. That is exactly what you would expect. But to do a more quantitative analysis, I think you need to actually get your hands on the details of the LIGO data, which I haven't done myself. Yeah.
So Masha will be around through the end of the day. She has two 30-minute slots open still at 2 and at 3 o'clock. So if anyone's interested, you can sign up for those. And now let's thank her again, please, for everything.